Gabriel Cramer, a very smart guy in the 18th century, found a quick way of solving linear equations using matrices. It's named after him and is called Cramer's rule. Let's see how it works. You know this equation? It's the same one from the first lesson of this section. From the same lesson, we know that x and y are the variables. The numbers next to them are coefficients, and of course, we have the constants on the right side. We make three matrices from the equations: a matrix of coefficients, a matrix of variables, and a matrix of constants. The coefficient matrix keeps the coefficients. The first column takes the coefficients of x, that is a and c. The second column is reserved for coefficients of y, that is b and d. X and y end up in the variable matrix, while m and n are used to make the matrix of constants. We can see three matrices. Label them: A for coefficients, x for variables, and b for constants. Ax equals b. So far, everything has been the same as the matrix inversion method. But now, I'm introducing two more matrices, Ax and Ay. Matrix Ax is the same as A, but the column containing the coefficients of x, the left one, is replaced by the column of constants. Similarly, Ay is also the same matrix as A, but here the column with the coefficients of y, the one on the right, is replaced by the column of constants. The Cramer's rule only needs these three matrices, A, Ax, Ay, to solve the equations and find the unknowns. The rule tells us that the variable x will be equal to the determinant of matrix Ax divided by the determinant of A. Similarly, variable y will be equal to the determinant of matrix Ay divided by the determinant of A. This is the Cramer's rule. But how did we even get these formulas? Are they really that simple? Yes, they are. Let me show you the proof. We had this Ax equals b, which can be converted to this x equals A inverse b, as we did previously. Now, the inverse of A is the adjoint of A divided by the determinant of A. So, x becomes this. Ignore the determinant right now and find the adjoint of A by interchanging the diagonal entries and changing the signs of the other entries. Then, put this adjoint and the matrix B in the formula. The determinant of A is placed as it is. Next, we have to multiply these two matrices on top. We will place the multiplication result in this 2 by 1 matrix. Multiply the first row of the adjoint of A by the first column of B. We get D by M minus B by N. Do the same for the second row, first column, to fill this position. We get negative C into M plus A multiplied by N. Take the determinant of A inside the matrix by putting it under both entries. Compare this matrix with this one. You can see x is equal to this and y is equal to this. Great. Now, park this result for a minute, bear with me for a few more steps, and you will be amazed how elegantly we prove these formulas. Come back here and take the determinant of matrix Ax. Cross multiply these two minus the product of these two. Is this the same as this? Yes. Now, we can replace dm minus bn with the determinant of Ax. Surprised? There's more. For matrix Ay, its determinant is A by n minus C into m, or negative C by m plus A into n, which is easier to compare. Because of equality, I can replace this with the determinant of Ay. This is how Cramer's rule is derived from the matrix inversion method to get these formulas. I am sure you found this fascinating. In the next lesson, you will be even more fascinated by how easy it is to apply.